If you've ever set foot in a high school chemistry or physics class, you've definitely met these four letters. PV equals nRT.
The ideal gas law. It's
Yeah.
probably the first and, the most elegant mathematical model of the world that most of us ever learned.
Right. It's simple. It works.
And it's the result of centuries of work, blending insights from Boyle, Charles, Avogadro. It's perfect, provided you're dealing with a gas that's low density, high temperature, and, ideal.
But that's the thing. The moment we step outside that classroom, the moment we look at actual cutting-edge engineering or extreme physics, that simple law gets completely abandoned.
It stops being a useful simplification and starts being just plain wrong.
Why? What's the core issue?
Because the ideal gas law is based on two really convenient but massive falsehoods. First, that gas molecules themselves take up zero physical space.
Which they obviously do.
And second, that they exert zero force on one another. No attraction, no repulsion. Under normal conditions, these things don't matter much. But you push the extremes, high pressure, low temperatures. And those falsehoods create huge errors.
Errors that can make an experiment worthless or a piece of tech fail.
Exactly.
And that's our mission for this deep dive. We're looking at sources that show exactly where and how PV-nRT fails. We're going to explore three totally different real-world scenarios.
We're going from the nanoscale engineering inside a modern hard disk drive
to the explosive chaos of a shockwave, and then all the way down to the quantum limits of pressure itself.
and we're going to show why engineers are forced to use wildly more complex equations to describe reality.
Okay, so let's break down that theoretical divide first. I think understanding why the ideal gas law works so well in the classroom is key to seeing why it fails so badly everywhere else.
Absolutely. The IGL is this perfect storm of classical insights. You have Boyle, who gives us that inverse pressure-volume relationship. You squish a gas, the pressure goes up.
Simple enough.
Then Charles gives us the volume-temperature link. You heat it, it expands.
And Avogadro.
Avogadro is the one who ties it all together by connecting the volume to the actual amount of gas, the number of moles. Put it all together, and you get PV-nRT.
But the whole framework rests on those assumptions we just mentioned. And we know for a fact that molecules have volume and they do interact.
Exactly. So the failure points are really clear. At super high pressures, the volume of the molecules themselves becomes, a pretty significant fraction of the container's volume.
So there's just less room to move around than the equation thinks there is.
Precisely. And at low temperatures, those attractive forces, the van der Waals forces, start to matter. The molecules slow down enough that they start to pull on each other, affecting their behavior.
Okay, so if the ideal gas law is broken, what's the first fix? What's the first step up in complexity?
That would be the van der Waals equation. It's really the first major step into real gas modeling. What van der Waals did was mathematically patch those two big failure points.
So how does it work conceptually? For those of us without a whiteboard.
We don't need one. Just think of two correction constants. Let's just call them A and B.
Okay, A and B.
The B constant corrects for molecular volume. It basically says the real volume available for the gas to move in is the container volume minus the volume of all the gas molecules. The available space is reduced.
That makes perfect sense. The molecules are like tiny billiard balls taking up space. So what about the A constant, the attractive forces?
A corrects the pressure. Think about it. If molecules are attracting each other, they're pulling each other back slightly, away from the walls.
So they don't hit the container walls as hard.
Right. The measured pressure is actually lower than it would be ideally. So van der Waals adds this attractive force factor back into the pressure term. It's a clever way to account for that stickiness.
So it's not really a new law, it's the ideal law, but with these two smart corrections that bring it much closer to reality.
That's it exactly. It's the classical bridge from that 17th century simplicity to the messy reality of modern engineering.
Okay, so now let's take that corrected theory and apply it to a place I bet most people would never expect to find advanced thermodynamics.
Which is?
Inside a hard disk drive.
Yes, specifically the newer drives that use heat-assisted magnetic recording, or HMR. This is a perfect example of nanoscale engineering where pressure gets pushed to the absolute limit.
You're talking about the gap between the read-write head and the spinning disk.
Exactly. The head doesn't touch the disk. It flies on a cushion of gas, an air bearing, that's just a few nanometers thick.
A few nanometers, and the pressure in that tiny gap.
It can easily top 50 atmospheres. That's almost 750 pounds per square inch.
Wow, and that's way, way outside the comfort zone of the ideal gas law.
Far, far outside.
Well, why does this matter so much inside a hard drive? I mean, at the end of the day, it's just air or maybe helium in there, right?
It matters for reliability. Specifically, it's about water vapor, humidity,
Ah, corrosion.
corrosion, lubricant transfer, heat dissipation. It's all affected by humidity. And to calculate the maximum amount of water vapor that can exist in that gap, the saturation vapor pressure, you absolutely cannot use the ideal gas model. You need a real gas model.
So do engineers just plug in the van der Waals equation, or do they need something even more advanced?
For this kind of precision, they usually go further. They use more sophisticated equations of state like Redlich-Kwong or Peng-Robinson. They're like extensions of the van der Waals idea, but they're much better at modeling how attraction depends on temperature.
That sounds complicated. Is the extra work really worth it? How big is the deviation we're actually talking about here?
While it's absolutely worth it, the deviation can be dramatic. These models use a concept called fugacity.
Fugacity, that sounds abstract.
It is a bit, but fugacity basically tells you the effective pressure of a real gas. It's a measure of how non-ideal it's being.
Okay, so what do these fugacity calculations show? Do all gases misbehave in the same way?
And that's where it gets really interesting. The difference between those A and B constants, attraction and volume, really starts to shine.
How so?
Well, the sources show that at moderate temperatures, say around 300 Kelvin, and at that high pressure, heavier gases like nitrogen or argon show huge deviations.
How huge?
We're talking about a more than a 100% increase in the calculated saturation pressure compared to the ideal model.
Wait, 100%. 100% deviation. Why is it so much worse for the heavier gases?
Because that increase is almost entirely driven by the intermolecular attractive forces, that A constant effect. The heavier molecules just attract the water molecules more strongly.
Which means you can pack way more humidity into that high-pressure state than the ideal gas law would ever predict.
And that is critical for predicting your risk of corrosion.
So what about lighter gases? I know some drives are filled with helium to reduce friction.
Helium is fascinating. It shows much less deviation at those moderate temperatures. But during the HAMR writing process, the temperature locally spikes to over 550 Kelvin.
Very high temperature.
And at that high temperature, helium's deviation actually increases significantly.
But wait, if the temperature is high, shouldn't attractive forces matter less because the molecules are moving too fast to interact?
Exactly. You've got it. At those temperatures, the attractive A constant becomes almost irrelevant. Instead, the finite volume of the molecules, the B constant, becomes the dominant factor.
So because the helium atoms are moving so fast in a confined space, they start bumping into each other more just because of their physical size?
Yes. The non-ideal behavior comes from physical interactions, not from attraction. It's just amazing that inside this common device, engineers have to figure out if molecular attraction or finite volume is the bigger threat to its lifespan.
We've seen how PV-nRT fails under high pressure in a stable system. But what happens when we just shatter thermodynamic equilibrium completely?
Now we're getting into extreme dynamics.
Right. Our next source takes us to shock waves propagating through really disparate gas mixtures.
This is the world of shock tubes. They're used to generate and study these incredibly high-speed events. The experiment we're looking at used a mixture of sulfur hexafluoride SF6 and helium.
That's about as different as you can get. SF6 is this incredibly dense, heavy gas, and helium is, well, helium.
The contrast is enormous. The molecular mass ratio is about 36.5 to 1. You can picture it as a mixture of bowling balls and ping pong balls.
And what happens when a shock wave slams into that mixture?
The whole system is thrown into chaos. The goal of the experiment was to measure the pressure and temperature just after the shock passed to see which classical gas mixture model worked best.
And what were the contenders?
The two classics. First, Dalton's law of partial pressures. It assumes total pressure is just the sum of the parts, which implies perfect, instant mixing.
And the second?
Amagat's law of partial volumes, which assumes total volume is the sum of the parts. A bit more like they're coexisting, but not perfectly mixed.
Given that the basic IGL is already flawed, I'm guessing these didn't do so well either.
That's an understatement. They failed spectacularly. Neither law could accurately predict the post-shock conditions, and the disagreement was way beyond any experimental error.
But it wasn't just that they failed, it was how they failed, right? It depended on the mix.
Exactly. This is the key finding. For the post-shock temperature, a 50-50 mixture seemed to follow Dalton's law better.
Okay.
But a 25-75 mixture, the one dominated by the light helium atoms, aligned better with Amagat's law. The laws weren't even consistently wrong. Their accuracy depended on the composition.
Which suggests the problem isn't the math in the models, it's the assumption they're both built on.
Which is thermodynamic equilibrium.
They assume that after the shock passes, everything just instantly settles into a new, stable state.
And a violent shock wave, especially in a mixture this unequal, completely shatters that assumption.
So if those equilibrium models are out, we have to look deeper. This is where the kinetic molecular theory comes in, right? To explain the failure.
Yes, KMT gives us the concept of relaxation time. Let's call it tau. It's the time a system needs to, return to statistical equilibrium after it's been disturbed.
And when a shock hits, every molecule gets disturbed, but they don't all respond at the same speed.
Not even close. The helium atoms are 36.5 times lighter than the SF6 molecules.
The ping pong balls versus the bowling balls.
It's the perfect analogy. When the shock front hits, the tiny helium atoms have almost no inertia. They accelerate instantly, collide, and reach their own new equilibrium very, very fast. The relaxation time is short.
While the SF6 molecules, the bowling balls, are still lumbering around, trying to catch up.
Exactly. The helium component has already stabilized, but the process of interspecies equilibration, where the light and heavy gases finally reach a single shared temperature, is slow.
And that lag, that difference in their internal clocks, is what the scientists were measuring.
Yes, that microscopic difference in response time is what shows up as the big systemic disagreement in the macroscopic measurements of pressure and temperature milliseconds after the shock.
It's a powerful idea. We think of a gas as this uniform thing, but in a state like this, the components are really behaving like individuals.
Absolutely. The failure here has nothing to do with attraction or volume, the van der Waals sixes. It's about speed and momentum. It forces us to accept that molecules are individuals, and when their masses are that different, the simple idea of a shared instant equilibrium just completely collapses.
We've gone from high pressure to high speed. Let's now go to the ultimate frontier, the quantum realm.
The most extreme conditions, extremely low temperatures and highly confined volumes, down at the nanoscale.
And this is where classical physics just hits a brick wall.
A complete wall. The moment a system is confined tightly enough or cooled down enough, the core idea that lets classical physics work, the concept of phase space, it just breaks down.
And phase space is that idea that you can define a particle's exact location and its exact momentum at the same time.
Precisely. And that is explicitly forbidden by Heisenberg's uncertainty principle. If you can't know both simultaneously, the whole mathematical framework of classical gas theory becomes useless.
So how do you model a gas when you can't use those fundamental tools?
You have to switch to models that incorporate what's called quantum phase space, or QPS. These are models for Fermi gases and Bose gases. And the change is mathematical, but the physical consequences are massive.
So what's the mathematical change?
In classical thermodynamics, you calculate things like internal energy by doing a continuous integral over that phase space. You're assuming a smooth, continuous range of energy levels.
Okay.
In the quantum models, you have to replace those integrals with discrete summations.
Discrete summation. So you're adding up specific, separate values instead of a smooth curve.
Yes, you're summing up quantized energy levels, which reflects the quantum nature of the gas. And this is most important when the gas is tightly confined because the container's geometry, its actual shape and size, gets explicitly factored into how those quantum levels are defined.
So the box isn't just holding the gas, it's actively dictating its thermodynamic behavior.
That is the key takeaway. And this leads to the most mind-bending result when it comes to pressure. For centuries, pressure has been a simple scalar, a single number.
Like 1 atmosphere or 50 atmospheres.
Yeah.
But in these confined quantum gases, what does pressure become?
Pressure is no longer a simple scalar. It becomes a diagonal pressure matrix.
A matrix. You're telling me pressure now has a geometry.
It does. The matrix describes what's called anisotropic pressure. Anisotropy just means it depends on direction. So in these systems, the pressure you measure along the x-axis might not be the same as the pressure along the y-axis.
What could possibly cause that?
It's the quantum stress from the boundaries. The container walls restrict the quantum states differently along each axis, which leads to unequal stress. That means the physical pressure is literally different depending on which direction you measure it.
That's incredible. We started with PV-nRT, a single number P on the left side, and we've ended with a 3x3 matrix just to describe the same concept.
And you only get that beautiful, simple relationship back when you go to the semi-classical limit high temperature, large volume. That's when those confinement effects vanish, and the pressure matrix finally collapses back down into a single, simple scalar value.
So what does this all mean for you, the listener? We started with the ideal gas law, An equation everyone learns, and we found that modern science makes it, well, worse than useless in three very different regimes.
To figure out the corrosion risk inside a hard drive, we needed corrections for molecular attraction and volume. To model a shock wave, we had to throw out the idea of equilibrium and think about molecular relaxation times.
And to understand matter at the absolute limits of cold and confinement, we had to discard classical physics entirely and describe pressure as a directional geometric matrix.
The so what here is that this complexity isn't just academic. We need these real gas models for everything from calculating refrigerant cycles to designing high-altitude combustion systems. The gap between the ideal theory and physical reality has to be bridged with these more complex models.
So here's a final thought to leave you with. The behavior of a gas is dictated by these invisible forces and constraints. The most fundamental physics, the uncertainty principle, the finite size of a molecule, the simple mass difference between two gases, those are the things that determine if a high school formula works or if you need a complex pressure matrix to safely design a critical piece of technology. How many subtle, unseen, real gas corrections are running the world around you right now?